Variations in tendon insertion. Considerable variation in human anatomical structure exists, including the points in which tendons are attached to bone. A person whose tendons are inserted on the bone further from the joint center should be able to lift heavier weights because muscle force acts through the longer moment arm and thus can produce greater torque around the joint. It is important, however, to recognize the trade-off involving the tendon insertion. The mechanical advantage gained by having tendons insert further from the joint center is accompanied by a loss in maximal speed because with a tendon inserted further from the joint center, the muscle has to contract more to make the joint move through a given range of motion. In other words, a given amount of muscle shortening results in less rotation of body segments about the joint, which translates into a loss of movement speed. When a hypothetical muscle shortens by a given amount, the joint rotates. However, if the muscle were inserted further from the joint center, as in figure 3.13b, the same amount of muscle shortening would bring about only 34 degrees of joint rotation because the geometry of the dynamic triangle, whose vertices are the muscle inserted in origin and the joint center of rotation. To produce a given joint rotational velocity, a muscle inserted further from the joint center must contract at a higher speed, in which it can generate less force due to the inverse force-velocity relationship of the muscle, described later in this chapter. Therefore, such a tendon arrangement reduces the muscle force capability during faster movements. One can see how relatively subtle individual differences in structure can result in various advantages and disadvantages. For slow movements such as powerlifting, tendon insertion further from the joint than normal can be advantageous, while for athletic activities occurring at high speed, such as hitting a tennis ball, the arrangement can be disadvantageous. Anatomical planes of the human body. Figure 3.14 depicts a person standing in the standard anatomical position. The body is erect, the arms down to the sides, and the palms face forward. Anatomically, views of the body as in magnetic resonance imaging are generally shown the sagittal, frontal, and transverse planes. Respectively slice the body into left, right, front, and back, upper, lower sections, not necessarily at the midpoint. The anatomical planes are also useful for describing the major body movements. Examples of exercise movements that take place in those planes including standing barbell curl, sagittal plane, standing lateral dumbbell raise, frontal plane, and dumbbell fly, transverse plane. Human strength and power. The terms strength and power are widely used to describe some important abilities that contribute to maximal human efforts in sport and other physical activities. Unfortunately, there is often little consistency in the way the terms are used. This section provides a scientific basis for understanding human strength and power and shows how various factors contribute to their manifestation. Basic definitions. Though it is widely accepted that strength is the ability to exert force, there is considerable disagreement on how strength should be measured. The weight that a person can lift is probably the oldest quantitative measurement of strength. Technological developments have popularized the use of isometric strength testing and more recently, isokinetic strength testing. All sports involve acceleration, change in velocity per unit time of the body. For some sports and implement, baseball, javelin, tennis, racket, as well, because of individual differences in the ability to exert force at different speeds, strength scores obtaining from isometric and low-speed lifting tests may have limited value predicting performance in sports, such as tennis or handball, that involves acceleration at high speed. That is why Newton and Kramer have suggested a more inclusive definition of strength, the maximum force that a muscle or muscle group can exert at a specific velocity. Although controlling and monitoring velocity during strength testing requires sophisticated equipment, the resulting strength scores are more meaningfully related to sport ability than static strength measures or maximum lifts. The limited meaning of isometric and low-speed strength scores have led to a heightened interest in power at a measurement of the ability to exert force at higher speeds. Outside of the scientific realm, power is loosely defined as force, energy, strength, and might. However, in physics, power is precisely defined as the time rate of doing work, where work is the product of force exerted on an object and the distance an object moves in the direction of the forces exerted. Quantitatively, work and power are defined as work equals force times distance, and power equals work divided by time. For all the equations in this chapter to work out correctly, consistent units must be used. In the system, international day units, the worldwide standard force is measured in newtons, distance in meters, work in joules, newton meters, N times M. Time in seconds and power in watts, joules. The appropriate SI units for the equations can be obtained from other common units using the force listed in tables 3.1. As an example of applying equation 3.1, the net work performed when a weight is lifted is equal to the magnitude of the weight manipulated by the vertical distance the weight is lifted, regardless of any horizontal excursion of the weight during the ascent or any variation in the speed in which the weight travels. For example, calculate the work involved in lifting a 100 kilogram, 220.5 barbell, 2 meters, 6.6 feet, the per repetition for 10 repetitions. Determine the weight of the bar in SI units, newtons, by measuring the mass of the bar in kilograms by the local acceleration due to gravity in meters per second squared. If the local acceleration to gravity is not available, 9.8 meters per second squared is a good approximation. Weight equals 9.8 meters per second squared times 100 kilograms equals 980 newtons. Apply equation 3.1 to calculate the work of 10 repetition in joules. Work equals 980 newton times 2 meters times 10 reps equals 19,600 joules. This method of calculating work can be very useful in quantifying the volume of a workout. The work of each set is calculated as shown, and the total work of the whole workout is determined for free weight lifts. The vertical travel of the bar for one repetition of each exercise is measured for each individual by subtracting the height of the bar relative to the floor at its low position from the height of the bar at its high position. For weight stacks exercises, the vertical travel of the stack is measured. These measurements can be made with an empty bar or lowest weight plate on the stack because the vertical distance traveled by the weight during the given exercise for an individual should be about the same regardless of the weight used. In the previous example in which work was determined, it takes about 40 seconds to perform 10 repetitions. The average power output in watts for the set is calculated using equation 3.2. Power equals 19,600 joules divided by 40 seconds equals 490 watts. The work and power equations just presented apply to an object moving from one location to another. Work and power are also required to start an object rotating about the axis or to change the velocity in which it rotates, even if the object as a whole does not move through the space at all. The angle in which an object rotates is called the angular displacement. The SI units in which the radian, rad, 1 rad equals 180 degrees divided by pi equals 57.3. Angular velocity is the object's rotational speed measured in radians per second, rad, divided by seconds. Torque is expressed in newton meters, N times M, but should not be confused with work, which is also expressed in newton meters. The difference is the distance components of the torque units refer to the length of the moment arm, which is perpendicular to the line of action of the force, while the distance component of work refers to the distance moved along the line of action of a force. Just as for movement through space, the work done in rotation of an object is measured in joules, the power in watts. The equation for rotational work equals torque times angular displacement. Figure 3.3 is used to calculate rotational power, just as it was used to calculate linear power. The discrepancy between the common scientifically determined definitions of power has led to misunderstandings. For example, in the sport of powerlifting, which involves high forces but relatively low movement speeds, less mechanical power is produced than in several other sports, including Olympic lifting. Despite the discrepancy, the sport of powerlifting is unlikely to be renamed. However, the strength and conditioning professionals should use the word power in all other contexts by only in its scientific sense to avoid ambiguity. Furthermore, although the word strength is associated with slow speeds and the word power with high speeds of movement, both variables reflect the ability to exert force at a given speed. Power is a direct mathematical function of force and velocity. Therefore, if any of the two variables, force, velocity, power, are known, the third can be calculated. If an individual can generate high force or high power at a particular velocity of movement, precisely the same ability is being described. That is, the ability to accelerate a mass as a particular speed. Therefore, it is not correct to associate strength with low speed and power with high speed. Strength is the capacity to exert force at any given speed, and power is the mathematical product of force and velocity at whatever the speed. What is critical is the ability to exert force at speeds characteristic of the sport to overcome gravity and accelerate the body or an implement. For the sports movement made relatively slow by high resistance, low speed strength is critical, whereas for a movement that is very fast due to low resistance, high speed strength is important. For example, when offensive and defensive football linemen push against each other, their speed movement is slowed by the muscular force exerted by the opposing player, as well as the inertia of the opposing player's body mass. Because the muscles are prevented from contracting at high speed, the ability to exert force and power at low speed is an important component of performance. In contrast, a badminton player's muscles quickly reach high velocity as a result of minimal inertial resistance of the lightweight racket and the player's arm. Therefore, the ability to exert force and power at high speed is critical to making rapid adjustments in a stroke.